Hello and welcome to Commonly Encountered Concepts in Clinical Data Science. I'm Nicholas Ponticus. I'm a computer scientist by training and a group leader at the UCL Institute of Ophthalmology. My team works in decision support systems for rare diseases. First, we'll start with some pre-unit quiz questions. So question 1 should be an easy one. Does a p-value less than 0.05 imply significance? Yes, no, sometimes. Pre-unit quiz question 2. Can you think of a counterexample for the statement correlation implies causation? Pre-unit quiz question 3. Is there a difference between a correlation and a regression? Okay, so learning objectives for this module are to understand how to critically interpret p-values, to understand how to critically interpret models, and understand more about modeling when applied to linear regression. So first we'll start with critically interpreting p-values. In particular, we're going to review some p-value fallacies, in particular around multiple testing, subgroup analysis, and winner's curse. So here we've got an example of the multiple testing problem. So this is nicely illustrated here by this comic. So here what we've got is 20 sequential tests that are repeated to test the association between the color of jelly beans and acne. Obviously two things which are very unlikely to be linked. 20 different colors of jelly beans are tested, and out of these 20 tests, 1 out of 20, which corresponds to 5%, has yielded a significant result, which is what is highlighted here, green jelly beans linked to acne in the headline. So, as you probably realize, what's happening here is if you repeat a test a number of times, then the more you repeat the test, the greater the chances of witnessing a significant association. So in this case, a p-value less than 5%. The chances of this increases with the number of tests repeated. So this is known as a type 1 error, or false positive. And since there's a 5% probability of doing this, if you're doing 20 tests, then 1 out of the 20 tests is likely to give you a 5% just by chance. So how do we get around this? So clearly you can think of it, you can probably think about it yourself. If you're repeating a test multiple times, then what's a logical way of working around this p-value threshold? Clearly we need a more stringent threshold, right? So that's what we're going to be doing. So if we look here, we want to correct these type 1 errors. And what we're doing here is using what's known as a Bonferroni correction. And this is very simply just dividing your threshold alpha here, which is 5%, by the number of tests performed. So if we're doing 20 tests, then we're dividing our 5% by 20, which gives us a lower threshold of 0.0025. So using this corrected threshold would have accounted for the number of tests that were done in the previous example. So we wouldn't have found this false positive association of green jelly beans linked to acne. However, this p-value fallacy of multiple testing is much more common than we think. A very easy way of falling into this problem of multiple testing is by doing subgroup analysis, something which is very common. I mean, in fact, subgroup analysis is important, as highlighted by the example there on the left, Simpson's paradox, which shows that you do need to look into different groups, in this case the blue and the orange group, for instance, to find a different association which is not visible when you look at the data set as a whole, as you can see in the black points there. This is a very common way. I mean, this is why subgroup analysis is important. But also subgroup analysis is kind of, I guess, taken advantage of in order to try and find significant results in your analysis. So in this little satire here, you see on the right there, you can see that people's sort of common approach to p-value interpretation. So trying to subset your data in a way to find a statistical significant p-value is known generally as p-hacking, and also more colloquially as a phishing expedition. And unfortunately, this is something we see in a lot of papers. A lot of people repeat this subgroup analysis, and they do that and they still use a threshold of 5%, and they do not account for the number of tests that are done. So this is quite common, and this is something you should be aware of. So for the previous reason that we just talked about, subgroup analysis, you might end up with people reporting spurious associations, or associations at least that are not very strongly statistically significant. So in order to do good science, we need to externally validate them, right? And the reason why external validation is important is because of this phenomenon known as winner's curse. So winner's curse is basically you only take the most significant results for an experiment, and you discard all the others. So that kind of overestimates the importance of these results. And then you're basically, it's a confirmation bias. If they've been reported once, they'll be reported again, and you keep on picking these winners each time, and you're kind of overestimating the effect of these parameters, or how significant they are, right? So I mean, what this picture is showing you here is that the actual value of an item is where that vertical line is, but the auction winner is obviously the one that's, in the case of an auction here, which is the example, that has paid the most, right, for it. So the price of the actual value of the item is going to be overestimated, right? So that's kind of the idea, right? So that's why we need to always externally validate our data, our findings, ideally to make sure that we haven't overestimated them from our data set, that we can replicate the findings. So now we're going to be talking about the limits of correlation. So the definition of correlation, according to Pearson, Pearson's correlation is this equation that you see here, which is the covariance of x and y divided by the square root of the variance of x multiplied by the variance of y. And clearly we know correlation does not imply causation, and here are examples of this, as you can see here on the right, looking at again some two things which clearly are not related: chickenpox incidents and names of individuals. Okay, so now we're going to talk about critically interpreting statistical models. So what is a statistical model? A statistical model is a mathematical representation that explains data. You will have heard of parametric and non-parametric models in the previous lectures. Here are examples of each in this table. So if the model is explicit, then that tends to be a parametric model. This usually is the underlying model is usually a normal distribution. So t-tests, pair t-tests, one-way ANOVA, and linear regression, which we'll be talking about more in this lecture, are examples of parametric models. On the other hand, non-parametric models, they tend to not have an explicit model underlying them, or they don't use a standard distribution, a normal distribution. So I mean, this is just one definition of parametric versus non-parametric. There may be other people use slightly different terminology, but that's the kind of general idea. And one key thing is that generally parametric models, they make certain assumptions about the data and how it was generated. So for example, that the observations are independent from each other. I think this applies across all models. And that they were generated from a normal distribution in the case of parametric models. So as I said, linear regression is the model that will be the parametric model that we will be talking about more in this lecture. But first I'll be talking more about some general properties of models before going into the linear regression example. So what makes a good model? A good model is a useful model, and this is a quote at the bottom from mathematician George Box. All models are wrong, but some are useful. And what do we define as utility? Well, usually the use of a model is to predict a label on unlabeled data, or to assess the statistical significance of a parameter. Another important feature of models is that they need to be able to generalize to new data. So as you can see here in the comic, you've got on the left an example of a linear regression, a straight line, which is a pretty sensible model, and on the right a more sort of creative but less useful model. And here is another extract from a comic. So all these extracts mostly come from the XKCD comic. And this shows different approaches to fitting models, some reasonable, some less so. Generally, the squiggliness of the line depends on the number of parameters of the model. So for instance, a linear model will have two parameters, a slope and an intercept. A quadratic model will have three. And generally, the squigglier the line, the more the parameters. So as you can see, the conclusions and the performance of the model that you draw from the model will be widely different depending on which model is applied. Generally, we abide to the principle of Occam's razor, which is the simplest model is the best. So this translates to a model with less parameters. So what does it mean to fit a model? So it means finding the optimal parameters, theta, that best fit the model. So there's two ways of going about it, of finding the optimal parameters, theta. We can either use the mean square error approach, and we're trying to minimize the mean square error, or the maximum likelihood estimation. And we're trying to maximize the maximum likelihood estimation. So for the error loss approach, what we've got here is an example of a linear regression, and here we're trying to minimize the error function. So we're trying to find the parameters theta, which in this case are the slope and the intercept of the linear regression, which minimizes the average squared sum of the red lines. So the red lines you can see here that are going from the purple dots to the blue line, these are the errors. We square the errors because some of the red lines are below the blue bar, so they're negative. So we don't want to the positive and the positive red lines and the negative red lines to cancel each other. So we square them, and then we take the mean of them. So that's the mean square error. And as I said, we're trying to find the parameters theta, which means the slope, and the intercept, which will minimize this mean square error. In the mean square error definition, you've got y, which is the actual y value of the purple dots, and then you've got the y at symbol, and that is actually the projection of the purple dots onto the blue line. So is what the model predicts to be the actual y value. So the difference between the y value, the predicted y value, and the actual y value is basically the distance, the length of the red lines. The other approach is the maximum likelihood approach, and here it's a kind of a different way of thinking about it. And here we're not using a linear regression example. What we're using here is firstly it's a one-dimensional data set, so those blue points are coming from one-dimensional, not two-dimensional, and we're trying to fit distributions to that data. The intuition here is that the way to think about it is that we are assuming that these points have been generated by one of these distributions. We've got different color distributions there. You can see the red, the green, the blue ones, and we're hypothesizing that the blue points have been generated by one of these distributions, and we want to see which one of these distributions is the most likely to have generated these points. So these distributions differ by their parameters theta. They're all normal distributions, by the way, and the only difference between them is the actual parameters theta, which in this case are the mean, so where is the distribution centered, and the variance, so the spread. And here, if you take, so the way to go about it is you take the blue points and you project them onto the distribution, and that tells you the probability of seeing that blue point under that distribution. And you get the probabilities from each of these points in that way, and then since all the observations are independent from each other, you multiply all the probabilities by each other, and that gives you the likelihood. And for practical reasons, because it's difficult to deal with a multiplication of probabilities, we take the logarithm of these probabilities. And as you know, when you take the logarithm of the probabilities, that turns into a sum. And so what you have there is the log likelihood function that you can see underneath that. The equation there is the log likelihood. And what you're trying to do is to find the theta parameters that maximize the log likelihood. So in the case of the distributions that we have here, probably the red one is the one that would maximize those parameters, because that would maximize the likelihood, because the blue points have the most weight with the red line, because it's the highest. It's giving the most weight to these points, right? So they'll have the higher probability from coming from the red distribution. So mean square error and maximum likelihood are different ways of thinking about the problem, but they are quite, the end result, it should be the same. Generally, the mean square error is sort of more simple and more intuitive way of thinking about it, and this is what we're going to be using in our example of linear regression. So the one thing to bear in mind is that in these examples I've given you, the number of model parameters are fixed. So in the example of the linear regression, we've got two parameters, which are slope and intercept. And in the example of the model fitting the normal distributions, we've also got two parameters, which are the mean and the variance. You can always make models more complicated by adding new parameters, as we're going to discuss. So one important concept to get your heads around is that the mean square error that we just discussed can be split into two types of errors, the variance and the bias. You don't need to know the ins and outs of this, how you derive this, but just think of it, just think of the bias as a systematic error and the variance as a random error. So in the next slide, I'm going to show you a more sort of intuitive way of thinking about it. So this is a pictorial representation of bias and noise, and variance. So bias, you can see here. I think it's fairly self-explanatory. A high bias. If you look at the top left, a high bias, low variance situation would be you'd be missing the bullseye, consistently missing the bullseye. So you'd have a systematic error, but you'd have very small random error. So your points are very clustered. Top right is obviously the worst case scenario, is where you have a high bias and high variance, a lot of spread, and you're consistently missing the mark. The bottom right would be a situation where you have a low bias but a high variance, so you are centered on the bullseye, but there's quite a lot of spread in the points. And then the best scenario is the bottom left, where you have low bias and low variance. And obviously that's the best kind of model you can get, but the best kind of model you can get where you minimize both the variance and the bias, but this is difficult to get. So in the context of model fitting, what is bias and variance? So in the first example, you can see what a high variance model will look like. So it would tend to overfit the data. So you've got a line that's going through every single point, meaning you have as many parameters in your model as you have data points. So if we try to apply the model to some new data, we would need to add more parameters to the model to fit those data, and so the model would be very, very unstable. On the other hand, if you had a high bias model that only has one parameter, as you can see in the second example, then the one parameter being the intercept, this model clearly doesn't do a very good job at fitting the data, and it's likely to get it consistently wrong. So this is what would known as a high bias model. The third one is, again, the best scenario. It's a low bias, low variance model, and this is fitted with in this example, with a quadratic function, so it probably has 3 parameters. However, this type of model is difficult to find, and we often have to compromise between the variance and the bias. However, the biggest problem usually is the first problem, which is of overfitting, because we are usually in a situation where we don't have a lot of data, and we tend to try and fit complicated models to simple data, or to data where we don't have enough observations. So how do we know that we're overfitting? So it's really important to have a training and a test set to know if you're overfitting. So if you're perfectly overfitting, this will mean that your training error is 0, but you have a high test error, meaning you've perfectly fitted your training data, but when we give you new data, then you're not able to generalize that new data, so you have a high test error. So as soon as you start seeing a divergence between the training error and the test error, as you can see in this picture here, then you know that you're starting to overfit. So training error will always go down as your model gets more complicated, because you'll be fitting the data better and better. But then you'll start seeing the test error creeping up, and that's a sign that your model does not generalize to new data. So again, just to discuss this in a bit more detail, the trade-off between a simple model with few parameters and a complex model with a large number of parameters. So if the model has many parameters as data points, then the model fits perfectly the data, but will not generalize to new data. So it overfits. And conversely, if the model has too few parameters and is too simple, then it will underfit. So this is a high bias, low variance model, whereas a model that overfits is a low bias, high variance model. So it's a trade-off between the model complexity and the model fit, and there is a sweet spot as illustrated by the plot on the right. And as you can see on this plot, the total error that is in black is the sum of a training error and a test error. So if the model is too complex, the total error will be high because of high test error, and if the model is too simple, then the total error will be high because of the training error. So we want to find this optimal point where we can try and both minimize training and the test error. So how do you get this balance between model complexity and model performance? If we define k to be the number of parameters in the model and n the number of data points, so obviously the first thing to bear in mind is that k, the number of parameters, must be smaller than n, the number of data points, because if it's the same, then you've overfitted. But how much smaller does it have to be? Well, there's several criteria you can apply. So here are a few of them: Bayesian, Akaike, and variance ratio are 3 of these examples. There are more. And what all of these criteria have in common is that they penalize for the number of parameters while trying to maximize the likelihood. So bear in mind that the likelihood is a number. The log likelihood is going to be a negative number, so the minus log likelihood would be a positive number here. So to illustrate how these methods work in practice, I've picked the variance ratio criterion as an example, and I've applied this to a problem which is finding the optimal number of parameters k, which in the case of this problem here is the number of clusters in your data. So this is we're not talking about linear regression here anymore. We're talking more about the example I gave you previously of trying to fit distributions to data. Except here we're not only trying to fit one distribution to the data. We're trying to fit several distributions to the data, which are the several clusters. And we've got an extra parameter, which is we've got the center and the spread of the clusters, but we've also got an extra parameter, which is the number of the clusters. And that's the parameter that we're going to try and see what is the optimal point for this parameter. So using the variance ratio criteria, the definition is actually similar to the mean square error definition in a way, in that we're comparing what's this SSB, which is the sum of squares between the clusters, with SSW, which is the sum of squares within the clusters, while penalizing for a large k. So you can see that from the definition, the way the denominator is defined, that if k equals n, then that will be 0 and that will be non-defined. So you can't have k equals n. And to show this in practice, we apply this on the data from figure B. And when you apply this to the data from figure B, you're looking at how the variance ratio criteria increases with number of clusters k, which is what you see in figure A there. So in figure A, we are trying to predict the optimal number k of clusters. And we find the optimal number of clusters to be the highest value for the variance ratio criterion, which is the red point in figure A. And this is defined as 5. And as you can see from the picture in B, this agrees with what we see. So this works. However, just to show you that things are not always as easy, as soon as you start adding some noise into the data and bringing the clusters closer together, then the variance ratio criteria has a much harder time of finding the optimal k. So what we've done is we've taken to create figure C, we've just taken the clusters from figure B, we've moved them a bit closer together, and we've added some more. We've increased the spread of the data. So this is still the same number of clusters. However, now you can see that the variance criterion is no longer 5, but it's 6. So it overestimated the number of clusters. So this highlights that these sort of methods might overestimate the number of parameters if the data is noisy. So now we're going to talk about linear regression in practice, so a model fitting in the context of linear regression. So linear regression is a parametric model, and like all parametric models, there are some assumptions which are linearity, so that the relationship between the x and the y values are linear. Homoscedasticity, which means that the variance of the residuals when you fit them is going to be the same for any value of x. This will be clearer as we'll discuss later. Independence, the values are independent from each other. The observations are independent from each other, they're not correlated to each other. And normality, that the residuals are normally distributed. So the residuals are, just to let you know, are the error terms basically. So for the error terms to be normally distributed, that also assumes that the underlying data, so the x and the y, are normally distributed as well. So in order to discuss linear regression, I'm going to use a specific data set, which is known as the Anscombe data set, also known as the Anscombe quartet, because it contains four two-dimensional data sets. So what is interesting about these four data sets is that, as you can see, they're plotted there. They all look very different from each other, yet they have the same statistical properties. So if you plot x1 against y1, x2 against y2, x3 against y3, and x4 against y4, they'll look completely different. But if you do a correlation on them, and if you look at their mean and their covariance, and you do linear regression, you get the same sort of estimates, the same parameters. So this is really illustrating why it's important to look at your data. And the reason why they have the same values is because the same parameters is because obviously the data has been, manufactured in a way to have this property. And what this exemplifies quite nicely is that you can see from the bottom two plots, there's 2 points which are massive outliers, so very far from all the other points, and those are the points which are really having a big effect on the parameters that we will be estimating. We will talk about this in more detail, but just make a mental note of these 2 points, which correspond to point 3 and point 8. So point 3 is an outlier for graph 4, and point 8 is an outlier for graph 3. So what is, just to give you some background of linear regression and understanding the theory of linear regression. So what you're trying to do linear regression, as I've mentioned previously when I was talking about mean square error, is that you are trying to draw a line through the points which minimizes this mean square error. So here I'm talking about the residual sum of squares, which is the same thing. It's basically the error terms, but we haven't done the average of them. So the mean square error is the mean of the residual sum of squares. And the important thing, another important statistical property is the variance explained, and that's known as the R squared. So what that is the error explained by the model, so the mean square error, divided by the variance in the data. So how much is your linear regression, how much of the variance is your linear regression explaining? So that's an important parameter, the R squared. So for the actual estimation of the slope and the intercept, so if you're doing a univariable linear regression, which we have here, two-dimensional, we just have 2 dimensions here, then you can calculate the slope yourself by hand. It's just the covariance of the y and the x divided by the variance of the x, and the intercept is defined as you can see there. And that we talked about correlation, and you can see that actually the formula for correlation for the Pearson correlation is quite similar to the formula for the slope, except that the denominator is slightly different. Instead of divided by the variance of x, we're dividing by the square root of the variance of x times the variance of y. And this is the output you see there at the bottom, is the output you would get from the R programming language. So it's very easy to apply linear regression in R. You just write this formula, LM, that as you can see there, and that will give you your, you do the summary of that, and that will give you all that output there. So it will give you the intercept, it will give you the slope, it will give you also the standard error of the intercept and the slope, and the significance. And it will also give you the F statistic. So the F statistic refers to the mean sum of square of the model divided by the mean square error. So it's basically how well the model fits overall. So it's related to the R squared value. But what's important, and I want to draw your attention to, is the statistic for the t-test, the t-value, which relates to the slope parameter. And the way that's obtained is by comparing the slope that we've obtained from our model to that of the null model. So the null model, as you can see there, would have a slope of 0 and an intercept, so it would just be a horizontal line, and the intercept of that horizontal line would be the mean of the y parameters that you're trying to explain with the x parameter. So what we're seeing here is that the slope is statistically significant. So that's using a t-test, as you've probably heard in a previous lecture about the t-test. So as you saw, you also had a standard error, and the standard error allows you to give from the standard error you can derive the confidence intervals. And the important thing to realize is that, as you're probably aware, is the standard error confidence intervals. How big the standard error is depends on it's proportional to how big your data set is, right? So the number of data points is inversely proportional to the square root of the standard error. And to get your confidence intervals, you can see there from the formula, that's how you get your confidence interval. Usually people are interested in the 95% confidence interval for the slope, and that's represented by the green band here. And what I'm showing you here is that if you've got 11 data points, then your green band, your confidence intervals are quite wide. If you've got 110 points, then they're much narrower, right? Much tighter. So you've got much more confidence on the actual parameter for the slope. And the confidence interval, and that's the formula for the confidence interval, and the Z is derived from the student distribution. And usually you pick the Z to represent a 95% confidence interval. Okay, so we've fit our distributions. We fit our linear regressions to the four data sets, right? The four Anscombe data sets, and this is what we get. These are the residuals, the errors, basically the error terms. So the way this is represented, the colors and the size of the points show how big the errors are. And what you can see is that the point in graph 3 we've highlighted previously is giving you a very big error term, right? And interestingly, what we see in the graph 4 is that the outlier seems to actually be driving the regression line, and so it has a tiny error. You can see there at the top right of the fourth graph, the bottom right there, you can see the fourth graph, that little point which is an outlier is actually driving the linear regression. So even though it's an outlier, it has no standard error because the line is going straight through it. So that's something we'll see later. This point has a very important influence, a big influence on the regression. So remember we're talking about the assumptions at the beginning, and we want to now see how well are these assumptions valid, and how well does the model, how appropriate is a linear regression to these data, right? As we've seen from the previous plots, we know that from graph 1, it looked like it was a pretty good fit, but it doesn't necessarily look like it's a very good fit for the other ones here. And so this is one of the methods we use to we plot the residuals versus the fitted values to kind of troubleshoot and see whether our linear regression is appropriate for this data, right? Whether the assumptions hold. So this is what we see when we plot the residuals, so the error terms versus the actual fitted values. And what we would like to see is what we see in the first graph, the top left one, which is that the residuals are randomly distributed around the y equals 0 line, right? So this suggests that the error terms are pretty much equal, right? And no one residual stands out here, suggesting there are no outliers. However, here you have a completely different pattern. Similarly here, and here you can see clearly that there's, we've got nothing here in the middle. So there's obviously it doesn't look quite right. Here we're showing, if you remember, this data set didn't really follow a linear pattern. It was more of a quadratic pattern, and I guess this is what you're seeing here. Another property of the residuals of these standard errors is that, if you remember from the assumptions, they should be normally distributed. And well, graph 1 looks good. They're pretty much normally distributed, or normalish, whereas the other graphs don't look so good. And in particular, graph 3, we can see a clear outlier here, which is this data point, if you remember, that we picked out. Another representation of this is doing what's known as a quantile plot. And since the residual should be normally distributed, what we are doing here is we're plotting the theoretical quantiles of a normal distribution on the x-axis against those from the residuals of our distribution. So we want the points to fall on a straight line, which they do in graph 1, the top left one, but less so in the others. And again, here we can see the clear outlier here. The scale location plot is another troubleshooting plot, and this tests the linear regression assumption of equal variance. So remember this homoscedasticity. So this is saying that whether the residuals have equal variance along the regression line. This is also known as a spread location plot. So if they do have equal variance, then the residuals should occupy equal space above and below the line. And this seems to be the case here, again for graph 1, but less so for the other graphs. So we wouldn't want, for instance, so this is showing you that if there's, as we're moving along here, whether there's more spread or less spread. So for instance, if all the points, which is kind of what we're seeing here, all the points are very close to the red line in the middle, but we're seeing more variance at the ends. And this is because of this quadratic sort of curve of the underlying data. So this is showing you that, in this case, homoscedasticity is not respected for this plot.
And finally, we're going to talk about the outliers. So we mentioned that in graph 4 we've got the outlier. In graph 3 and 4 we have outliers. And one important thing about outliers is that they have big leverage on the data, on the regression, and on any model they'll tend to have a big impact on the model. It'll depend on the model you apply, but for linear regression certainly it's the case that they have a very big impact. So how do we measure this impact? So we call this impact leverage, and we have a definition for leverage, which is the Cook's distance. And what this definition is represented here, and that is basically what is the impact on the model of removing the sample, so removing the data point I from the regression. So what you're seeing here is the yj and the yj with I removed. So for each data point you've got the predicted value with the model with all the points in them, and the predicted value with all the points minus the I point. And then we're looking and we're seeing, how big is that difference. So that's what we're going to see in the next slide here. So this plot can be used to find influential cases in the data set. So as I said, it's an influential case is a data point is one with a high leverage, and if we remove this data point, then the model will change a lot. So the slope of the model would change a lot. So the important thing, so I mentioned the influential data points tend to be outliers, but they may not always be outliers. So the point of this chart is also to highlight our data points which have high leverage more generally. So the way to read this is if you see something in the top right or inside the red dashed line or the bottom left, then that will have a high. These data points will have a high distance, a high leverage, which is measured as Cook's distance. So what we see in here, actually, when I plotted this, there was an error message, and that was telling you that the observation 8, which is the one which is actually driving the whole linear regression for that graph, well, that one actually it has such a high, has the maximum Cook's distance possible, which is 1, and that's not even plotted, so because it's out of scope, but that message was printed out. So clearly this confirms what we saw, and what was obvious is that that data point is basically driving the whole, has a massive effect on the model, and is driving the linear regression. And in fact, what I'm showing you here is if we remove that data point, well, that's what the model looks like basically on the right. So it's not even it's basically just a vertical line now. We don't have that regression line anymore. So the slope's gone from semi-inclined slope to a completely vertical slope, right? So anyway, to summarize what we've seen about univariable linear regression. So we talked about the statistical significance of the model parameters given by the t-distribution. We talked a bit about the model fit and how that's explained with the r-squared. And I showed you how outliers can have a big effect, so you have to be careful with outliers, and you have to decide what to do with outliers, whether to keep them or not, or whether to try and build a model that can account for outliers so it doesn't give them too much weight. And also we've gone through the assumptions and how to check them. So I've talked about how to check them with these troubleshooting plots that I just described. Okay, next I'm going to talk to you about multivariable linear regression in practice. So for this I'm going to use a, first multivariable regression. So same thing as univariable regression, but obviously multiple dimensions. What you're seeing here is basically if you had 3 dimensions, so you have 2 explanatory variables x1 and x2, and you have your y variable that you're trying to predict. There's always one one-dimensional variable that you're predicting, but you have many dimensions of explanatory variables. So that's what it would look like. It's no longer a line, it's a plane, it's a hyperplane, and you're looking at the distance of points from the hyperplane. If you want to start looking at 4 dimensions, 5 dimensions, then if you've got more variables to put in, then it gets a bit difficult to visualize that. Now we're working with multiple dimensions, we need to start working with matrices. And so I'm not going to go into the matrix algebra, but basically these are the definitions. The beta definition is you need to transpose your X matrix and invert it, and that's how you get the beta estimates. So it's going to be a vector of betas, because you're going to get as many slope parameters as you have variables. And the residual sum of squares is defined in that way. So the data, we're going to use a example data set here, and the example data set I'm going to use is a data set we've collected recently, which is a data set of our participants that have been using a home vision monitoring app, and what we're interested in predicting is how much they engage with the app, and that is basically how much they've used the app over a certain period of time. So how the frequency of use. So it's a number between 0 and 1, and the distribution of that. The histogram here represents that what that data looks like. So that's the predictor. That's what we want to predict, right? And other variables that we've measured in our data set are categorical variables such as the sex and ethnicity of the participants, and a numeric variable such as age and visual acuity of the participants. And also some of the participants also answered the survey. So I'm not going to do the analysis of this data set, but I am going to talk to you about certain things that you need to be aware of now when you're dealing with multivariable regression. And the first thing that you need to be aware of is collinearity. So what is collinearity? So you've got all these variables. Well, what happens when you have explanatory variables that are highly correlated? So that's something you need to be aware of, because you can't just throw in all your variables into your model and do a linear regression of all of them, especially if you've highly correlated ones. And what happens if you have highly correlated ones? Well, what's going to happen is that the coefficients will be very sensitive to small changes in the model, and if they are completely collinear, the variables, then the slope can't even be computed. You can't even compute the parameters for those variables. So you'll have to remove very collinear variables, or you'll have to try and find a way of combining the variables together to reduce the number of variables. And that's what you can do with principal component analysis or partial least square regression. But we're not going to go into that. I'm just naming these approaches. And I just want to show what collinearity looks like. So what you're seeing here is an example of collinearity. What I've plotted here is different visual acuity measures, and I've plotted them against each other. So when you can see a completely straight line, as you can see here, that's basically collinear. So that variable and that variable are completely collinear, and so are this variable and that one. So yeah, if you put those in the model, it's not going to work very well, as I'm going to show you. So this is what happens when you put them in the model. So as you can see here, they haven't even been, I've put them in R and I've done the linear regression. So I've added all these variables in the model here, and as you can see, it doesn't even can't even estimate the parameters. So that's basically showing you, why you can't have completely collinear variables. If they are subtly collinear, then that's okay, but it's still not great because it would be difficult to disentangle them and to get meaningful parameters. But anyway, this is what you get once I remove them. Then you get a more you are able to compute all the other parameters. So that's just something to be aware of. The other thing to be aware of is when you are putting your variables in your model, how do you represent them? So if it's numeric variables, then that's easy. Age, for instance, that's you don't need to do anything. But some variables may appear as categorical, but actually have some order to them, right? So it's always better to order your variables if you can. So if there's a natural ordering, if a variable has a natural ordering, then try and code it. So try and change the values into numeric values, so that you can have that coding. So that relationship, that ordering. The regression will work better if you can do that. If there's no ordering, then use what's known as factors in R and R will treat them as separate variables basically. So just to get you thinking a bit about coding, so a perfect example of variables that would need to be coded is, I mentioned there was a survey in our data, so we had to code the variables of our survey because they were like categorical variables. So out of these questions, try and think about how you would code them. So, for instance, question 5 of our survey was, how has using the app to test your vision made you feel? So that was on a scale. So we had a scale from 0 to 5. So we made sure to make that into numeric and code that. Second question already tells you that it's on a scale from 1 to 5. So that's clearly going to be numerical. Level of comfort with modern technologies. Again, you could try and represent that numerically. And your highest level of education. So that's going to be categorical, but you can try and represent that numerically. And I always recommend trying to translate categorical variables into numeric variables where there's some ordering and it makes sense. So next I'm going to show you what you would get if you were to just put in a categorical variable without coding it. So that's one of our questions, for instance, here. Which I've put in here, and what you can see here is that I think that's question 6, and what you can see here is that it's treated each of the answers. So the question 6 had 5 levels, which were 0.25, 0.5, 0.75, and 1, but they're represented as factors, right? They haven't been translated into numeric values. And it's treating them as separate variables basically, right? So it's, even though you're putting in one variable, which is your question 6 variable, it's the factors, it's treating them as separate factors. So it's looking at, okay, so the question 6 answer versus all the other answers. So 0.25, the first one, versus all the other answers, that's one variable. Second variable is question those who answered 0.5 at that question versus all the others. Is it trying to fit all of these separately as separate variables. So clearly that's not great. So a better way of doing it is to translate into numeric values. So what we just did is applied. It was already coded as digits, so we just made it from a factor into numeric. And the advantage of doing that as well is that now we've got something which might be significant, borderline significant. So this is showing you that basically, you lose power to detect significant effects if you don't code your variables properly. Okay, so that's variable coding. And then the other thing I want to talk to you about is another property of a multivariable regression that you need to be aware of is the interaction between variables. So what is an interaction term? You might come across that. So I like to say that's something quite rare. And people don't usually work with interaction terms too much because they're a bit confusing to work with, to be honest. And they make your model very complicated and difficult to explain. So you lose, you sacrifice model explainability by introducing interaction terms. But sometimes they can make sense. So what is an interaction term? An interaction term is basically a new variable that you'll create. And you create this new variable by multiplying two other variables or taking a cross product of two other variables if they are categorical variables. So in our example, in our previous example, you can imagine there might be an interaction multiplicative effect between age, sex, and comfort with modern technologies, or some other question. So something where there's some sort of, some sort of interaction going on. A bit like if you remember earlier in the presentation, I talked to you about the Simpsons paradox. So in different subgroups, you would see sort of different trends, kind of that idea. But I'm just going to make it concrete. I'm going to show you an example here, specifically of what I just mentioned of age, sex, and answers to question 10. So what we're seeing here is these different facets. So by the way, you can produce these sort of plots yourself by using this R package here. And what you're seeing here is different facets are basically each facet is a different answer to question 10. And the red and the blue are the male and female. And what you're seeing in the x-axis is the age, and the y-axis is what we're trying to predict, which is the engagement. And so what we're seeing here is that for those that answered 0 to question 10, meaning that they had little comfort with technology, then we see that it seems it's not significant because the confidence intervals are huge, probably because there's not that much data in that category. But anyway, what we are seeing here, for the sake of the example, is that there's decrease in engagement for males with increasing age, but there seems to be an increase for females with increasing age of the people that said they were not comfortable with technology. And as you go further into the more comfortable with technology, you see they tend to they follow the same trend. So actually, interestingly, older people tend to engage more with the technology if they're more comfortable with if they're more comfortable with the technology. That's intuitive, but they also tend to be more engaged with age as well, which is maybe not intuitive. But anyway, this is showing you that basically there's some interaction going on here, because we're seeing a different pattern here than we're seeing here. Although, as I said, this is not highly significant results. But that's just a general idea of interaction, just so that you know what interactions are about, interaction between variables. Okay, so practical tips about multiple regression. So we didn't go through an example of multiple regression, but one thing, it's basically quite straightforward in R. You just you can just write it in one line. You call the lm function and you pass in your parameters. But one mistake people commonly make and is to just try and throw in all your data into a multivariable regression. And the problem with doing that is that it makes it difficult to justify your approach. So firstly, because outcomes ratios that we mentioned try and go for the simplest model first, and then also because when you start putting all your variables in at the same time, there are some, because you're doing the covariance, if you remember, of all those variables, they might be interacting in different ways, and so you might end up with some significant results and others not significant, and it won't be very stable. So if you then put in your parameters and you remove a parameter, you might see things might change quite a bit. So and then you will have a hard time, justifying like what, how can you generalize this model to something else, right? So the approach I prefer is to univariably include your models, your variables one by one, and see which ones are statistically significant, and then take all the ones that are statistically significant and then put them in your model, in your multivariable model. And then see which ones remain statistically significant, because the multivariable model will take into account the covariance between the relationship between the different variables. So I'm just reading, but exactly the point I made. The general approach, keep it simple, and then try and build a more complicated model. But start with a simple model. And model validation. As we discussed, external validation is really important. So if you're lucky enough to have an external data set, then that's great. Use it. Obviously, don't train your model on the external data set. Keep it separate. If you do not have an external data set, then you can do cross-validation or bootstrapping, which is a way of splitting your data into training and testing, and taking different subsets of your data and repeating this training and testing on different subsets of your data, and then getting multiple estimates of your slope parameters, and then taking the average of them and looking at the spread. So that's one way of doing your internal sort of validation, but it's not a replacement for external validation. External validation is the best if you can have that data. So I think it's always great, and your any sort of publication and research that you'll do, if it has an external validation data set, then obviously it will be a much higher impact journal and a much more valid result. Especially considering the fallacy of winner's curse that I previously mentioned to you. So that's it. So just to summarize, you've understood how you should understand now how p-values are derived and can be interpreted. You've heard about the p-value fallacy. I've explained to you that in some detail. Model fitting, the trade-off between bias, underfitting and overfitting high variance models. Linear regression correlation, how they're derived. I've shown you the equation of how to derive them univariably, and you don't have to know how to derive them yourselves anyway. You can just use the R programming language for this, but you've understood how they're used, the context, the assumptions that are made, and how you can troubleshoot you can visualize your data to troubleshoot it and to make sure that the assumptions are not violated. Be aware of outliers in your data, because your outliers can have a massive influence on your model, especially if you're doing a linear regression. And I've talked to you about a few concepts of multiple regression to be aware of, in particular the concept of collinearity and interaction, and also how to code your variables, right? Okay. And next, we're gonna go to the quiz. The quiz.
So this post-unit quiz, question 1. So Pearson correlation expects variables to have a linear relationship. Is that true or false? What is the impact of collinearity? Is it unstable parameters? Is it stable parameters? Is it non-computable parameters? Which of the following models is likely to be most useful? A high performance on the training data set, moderate performance on the test data set, and low performance on the external validation data set, or moderate performance on the training data set, moderate performance on the test data set, and moderate performance on the external validation data set. Post-unit quiz question 4. What is linear regression? When is linear regression not appropriate or misleading? Is it 1, when the outcome variable is not numeric? 2, when the predictive variables are not normally distributed? 3, when they are outliers. Post-unit question 5. Which of these parameters, what is the variance explained? Which of these parameters is the variance explained? Is it 1 beta? Is it 2 r squared? Is it 3 y at? And finally, here's a list of references and further reading for you. I especially recommend this book, The Elements of Statistical Learning. It's free to download online, the PDF. It's a very nice book. It gives you good understanding and overview of machine learning and statistics. Great. Okay, thank you very much. Hope you all have a nice day. Bye-bye.